Welcome back once again to Mrs. Thompson's classroom. Today we're going to do more rational functions. In today's lesson, we're going to be graphing these functions, and we'll actually talk a little bit about these slant asymptotes that we didn't get to last time. Okay, so let's take this first example. First thing we notice is that this is a transformation of just 1 over x. Okay, so that means that this minus 1 means I have been moved to the right 1, and I have a vertical stretch by 2. Now, what is that going to do? Well, that means that my vertical asymptote is now going to be at x equals 1 because this one had a vertical asymptote at x equals 0. So I can mark that. Okay. The other way to think about that is, other than just using the transformations, is to remember that this denominator, set it equal to 0, will get me my vertical asymptote. So that means x equals 1 is the vertical asymptote. Okay, take the denominator, set it equal to 0. That also means my domain is x not equal to 1. Okay. Now, we also know that this graph right here goes through the point 1, 1. So if I'm going to move that to the right 1, it'll be at 2, 1, and it's been vertically stretched by 2, so now it'll be right here. Okay. The other thing you can do, of course, is just set up a table of values. Since I know the vertical asymptote is at 1, I might want to put in -1 and 0, and then 2 and 3. And that'll get me enough information to plot the graph. So if I put in a 1, I get -1, I get 2 over -2, so that's -1. So that's right there. If I put in a 0, I get 2 over -1, so I'll have a point here. Okay, if I plug in a 2, I get 2. We already have that point. And then if I plug in a 3, I get 2 over 2, which is 1. And then we can connect the dots. We know that it's going to go towards that asymptote, and we know that it has a horizontal asymptote at y equals 0. You remember from our last video, we talked about the ocean and spit. And in this particular problem, my ocean is on the bottom, my spit is on the top. So I have a 0 as my asymptote. So there is our graph. Okay, let's do another one. In this case, I've now moved it to the left 2. I have flipped it over the x-axis, and I've moved it down 1. Okay? So we should end up, when we're done, that means I'm going to have my vertical asymptote at -2. Okay? It is also a square. That means they're both going in the same direction, so they're going to be going, I'm going to be doing something like this. Okay, so let's get down to the specifics of it. X plus 2 squared equals 0 tells me that x equals -2 is my vertical asymptote. Okay, so that's here. So that's the first thing I do anytime I want to graph one of these, is I mark that asymptote. Okay, then we're going to find our horizontal asymptote by looking at just this part first. This is spit over ocean. So that means this goes towards 0. That means if I take this and I subtract 1, now I'm going towards 0 minus 1. So my horizontal asymptote is at y equals -1. So that's going to be here. Okay. Now we can just make a table of values to make sure we get it all in the right place. So because this vertical asymptote's at -2, I'm going to plug in -4, -3, and -1 and 0. Numbers near that asymptote will give me enough detail. Okay, so if I put in -4, I'm going to get -1 over -2 squared minus 1. So when I'm done with that, that's going to get me -1/4 minus 1, so that's -5/4. So that is going to be right about here. Okay, if I plug in the -3, I get -1 minus 1, so that's going to be at -2. And so this is going to come down towards that asymptote, and then it's going to go out towards the horizontal asymptote. If I plug in -1, I'm going to get the same thing at -2. Okay, and if I plug in 0, I'm going to get -1/4 minus 1, so that's -5/4 again. And then again, I'm going to go towards those asymptotes. And there's my graph. And we can see it has been flipped over. It's been moved left 2, and it's been moved down 1. So we got sort of what I started with. Remember, y equals 1 over x squared was the base function, and it looks like this. Okay, let's do one more. But let's talk about just general strategies. Now that we've done 2 of these, the first thing we want to do is we want to find the domain and plot the asymptotes. Okay, so vertical, horizontal, and our slant, and we'll talk about those in a minute. We want to find holes if there are any, and we'll talk about that. Find the intercepts, and then create a table to fill in the detail. Okay, so domain, asymptotes, holes, intercepts, and then fill in the detail as needed. Okay. All right, so let's take a look at this one. So again, let's find the domain. So the first thing I do is I try to reduce this, which it does not, but I can factor the denominator. So that tells me that x minus 3 cannot be 0, and x plus 3 cannot be 0. So my domain is x not equal to 3 and -3. Now, because the function did not reduce at all, that also means my vertical asymptotes are at x equals 3 and -3. Okay, my horizontal asymptote, if we look here, this situation is an ocean over ocean. So as x gets huge, all I'm concerned about are those largest exponents. So this is going to reduce to 2. So my horizontal asymptote is at y equals 2. Okay, so let's plot that. So here's -3. And +3. and my horizontal asymptote. Okay, so I got that part. Now let's find our intercepts. Okay, because it doesn't reduce, we have no holes. Okay, we'll talk about the holes in a minute. So let's now find the x-intercept. The x-intercept is where the function equals 0. So that means this fraction equals 0, which means the numerator equals 0. So then we just get x equals 0. So I plot this point right here. Okay. The y-intercept is where x is 0. So I plug in a 0. And in this case, I get that same point at 0, 0. Okay, so now that I have those, now we're just going to make a chart to fill in some details. So I need details on the left of this asymptote, in between the two asymptotes, and to the right. So I need to plug in at least a -4, maybe a -2, a +2, and a 4 at bare minimum. Okay, so if I put in a -4, we'll get 2 times 16 over 16 minus 9. So that's going to get us 32 over 17. Okay, so that's just a little less than 2. 34 over 17 would be 2. So just a little less than 2. So it's going to be about right here. That tells me that this is going to approach this asymptote here, and it's going to come down like this. Just having that one point gave me a little bit of information. Now you could get more points, like you could plug in -3.5 and -5, and you could get more detail there. Okay, now if I plug in -2, I'm going to get 2 times 4 over 4 minus 9. So the end result of that is 8 over -5. So that's a -8/5 or -1 3/5. So that would be, here's -1, -1 3/5. So about right. Okay. Okay, so this is probably going to come down towards this asymptote. It has to connect to that intercept that we plotted already. And now let's plug in a +2. Well, a +2 is actually going to do the same thing. And so it's going to be about right here. So it's going to connect to this 0 and then come towards the asymptote. And then let's plug in a 4. So we'll get 2 times 16 over 16 minus 9. So we get that 32 over 17 again. And we get that point about right here. And it's going to go towards the asymptotes. Okay. Now, just to note some options, when you have 2 vertical asymptotes, the outer parts over here and here, these outer parts are always going to get trapped like this and, act like they're coming towards these asymptotes. In between the two might look like a parabola like this one, although it's getting trapped by these asymptotes like a parabola does not, but it has that shape. Okay, or it might end up looking more like a cubic, but those really are your options. Okay, notice though that if it's a cubic, it could cross this horizontal asymptote in here near the center of the graph, and that is okay. The horizontal asymptote only concerns itself with what is going on the outer edge of the graph. Okay. All right, let's talk about those slant asymptotes. The slant ones occur only when the numerator's degree is one more than the denominator. Okay, so to find it, we're actually going to do the division. So the easiest thing is to go back to our synthetic division. If this denominator, of course, is not linear, you would have to use long division. So I'm going to bring down the 1, multiply by 2, add, multiply by 2, and I add. So this would end up being x plus 6 plus 15 over x minus 2 if I did the division. This non-remainder part, the whole number part that we got from the division, is the slant asymptote. So it's y equals x plus 6. The remainder is just telling me how close the function is to that line. Okay? And we also just note that these are also called oblique. An oblique line is just a slanted line. Okay? All right, so you're just going to divide and ignore the remainder, and that will tell you the line that the function is approaching. So let's take a look at this function. We notice right away that the degree is 1 larger. But let's go through the process. So the first thing I do is I try to reduce the function, which it does not. Okay, it doesn't reduce. So then I'm going to take the denominator and set it equal to 0, and that would tell me that my domain is x not equal to 2. Okay, that means my vertical asymptote is at x equals 2. Horizontal asymptote, there is none, because I have ocean over spit. Okay, the x squared is on top, so I have none. Okay, my slanted asymptote is going to come from doing that division. So I'll put the 2, and I'll put 1, 4, and 3, use those coefficients from the numerator, do the division, which is the same problem we just had. So my slanted asymptote is y equals 1x plus 6, and it had a remainder of 15. Okay, so now to plot these asymptotes, so x equals 2 is here. Okay. Y equals x plus 6. I'm going to have to extend my graph up a little bit. Actually, let's just do this. I'll change my grid. Okay, so x plus 6 has a slope of 1. So the slanted asymptote is going to go like this. Okay. All right, and so then let's find our intercepts. So the x-intercept, again, is where the numerator equals 0. So that factored. So I have -3 and -1. Hold on. Oh, yeah. Okay, -1, -2, -3. Remember, we changed our grid here. So -1 and -3. Okay. All right. And that means I need to fix this. Okay, 2. Okay, there. Now our grid is all correct. Okay, so now what we need to do is find the y-intercept. Now the y-intercept is just where x is 0. So that means I'll get 0 plus 3 over 0 minus 2. So I get -3/2. So that's right here. So right away I have enough information on this side to connect these dots. Remember, the graph is going to go towards those asymptotes. Okay? So all I really need to do to fill in some data, some detail, is to plot numbers like 3 and 4 and 5 and get some information over here on the right. So if I plug in a 3, I'll get 9 plus 12 plus 3 over 3 minus 2, which gives me 24 over 1. So that point is going to be way up here at 324. Okay? If I plug in a 4, I'm going to get 16 plus 16 plus 3 over 4 minus 2. So that's going to be 35 over 2, which is 17.5. So that's still going to be way up here. And then if we plug in the 5, we're going to get 48 over 3, which is 16. And so this function is going to track through those 3 points, and then it has to come back towards that asymptote. Okay? Now on these graphs where we have the slant asymptotes, our option is a picture like I just got, or it might get trapped in here. But either the black or the red that I just sort of sketched in there are the options for the shapes we might be looking for. Okay? This one is, of course, the black that we got. Okay? All right. Let's look at an application question. Actually, we're not going to do that one. I do want to point out holes, though. In order for one of these functions to have a hole, so in order to get a hole, what is going to happen is you're going to have a function like x plus 2 over x squared minus 4. So this is going to reduce. Okay. Right? So the one that reduces gives me a hole at x equals -2. The one that stays gives me that vertical asymptote at x equals a +2. And then once I reduce this function, I can find the hole by putting it in 1 over x plus, that is a minus, x minus 2 gives me 1 over -4. So the hole is actually at this point. Now, if you graph these on your graphing calculator, you're not going to see the hole. You're going to have to inspect a little bit, and you're going to have to trust the fact that you know there is a hole there. Okay, so the only time the holes happen is when we get a factor that reduces out. Okay, and then the reduced function will tell you where the hole is. Okay, all right, we will see you next time. And if you're in class with me, Monday we're going to be going through this together, and you're going to get some time to practice on these things. But hopefully this helps. See you later.